So presently we are learning the topic of Bellman Ford algorithm, and in our previous lectures we looked into what actually Bellman Ford algorithm is for, and how does it is different from how it is different from other algorithms for the same particular problem, we can say. So let us take a quick recap of what we have studied so far, and then we will proceed further with the agenda of today's lecture. So Bellman Ford algorithm, it is a shortest path. It is there to find the shortest path between different vertices in a particular graph, and this can solve the version of single source shortest path problem, but with a peculiarity that it is able to accommodate the edge weights which are negative, but not the negative weight cycle. So if a graph contains a negative weight cycle which is reachable from a particular source vertex, let us say S, we will be saying that shortest path weights are not well defined, but if it contains a negative weight cycle reachable from sources, then it contains no negative cycles which are reachable from the source, then it the problem remains well defined. While if we talk about Dijkstra's algorithm is not able to handle negative weight edges. So why we will say that the problem is not well defined, because no path from the source vertex to a vertex on a cycle with negative weight can be shortest path, as you take one more movement or one more iteration through that particular cycle, and it's a negative weight cycle, so you will be having a path with the lower weight, and then you keep on traversing in that particular cycle only, and every time you will be having a lower weight as compared to the previous one. We'll say that the problem is not well defined if it is a negative weight cycle. Now, how this Bellman Ford works? This Bellman Ford algorithm works. It first overestimates the length of the path, and then it keeps on relaxing, or it keeps on reducing, we can say, this overestimated path. And for this there were two sub we can say sub procedures. So one procedure was the initialize the graph. So initialization of graphs here means that the distance of every vertex v belonging to the vertex set from the source vertex S is going to be infinite. So this is a kind of an overestimate to the distance, and then we will keep on relaxing it, and then v dot pi, which is nothing but the predecessor, is nil. So predecessor is the just is the node just before in the walk. So this is the initialized single source sub function which we are going to call when we use Bellman Ford algorithm. Apart from that, after this it iteratively relax the estimates by finding new paths. Obviously the new paths are shorter than the previously overestimated paths, and by doing this repeatedly for all the vertices, we are going to guarantee that the result is optimized. And then the next kind of procedure which I am talking about was the procedure of relaxation. So here is the figure which explains the relaxation. So this says the distance of v from S, presently it is 9 and for u it is 5, but if we take a path from u to v, the total can be updated to 7, that is 5 plus 2 instead of 9, while in the next figure if it is 6 already, then upgrading it to 7 is not going to help us. So we will not relax this edge uv with the weight w. So this is actually the one figure is explaining the relaxation, or one figure is showing the relaxation, another one is showing when relaxation is not actually kind of helping us. So these are the things which we have already I can say we have covered in a lot more detail in our previous lecture. Now Bellman Ford, now let us take this further. Bellman Ford algorithm, basically it returns a Boolean value which indicates whether there is a negative cycle that is reachable from S. If there is such cycle, that means if the value of that Boolean variable is true, that means the cycle is existing. The algorithm indicates that no solution exists, and if there is no such cycle, the algorithm will give you the shortest path and also their weights, and that we have seen in our previous lecture, that that both the things, that is the shortest path, also the weight of the shortest path is going to be kind of given by this Bellman Ford algorithm. And the procedure here is to relax the edges, progressively decreasing the estimate v dot d until it achieves the the minimum weight, or we can say the shortest path, and the algorithm returns true if and only if graph contains no negative weight cycle that are reachable from the S, from the any source vertex. Here I am assuming S. Otherwise it will return false. That means the problem is actually not we can say well defined. So here let us take a graph and try to understand that how this relaxation or how these things are happening. So here we are going to give the representation to this graph. This is having total 5 nodes starting from 0 to 4. So the value of v is 5, source node is the 0, and in between you have 5 here, whatever the edges are. So between 1 and 3 you have an edge, weight is 2, between 4 and 3 you have an edge and the weight is -1, and please remember that this is a directed graph. From 2 to 4 we have an edge which is having 1, from 1 to 2 it is having weight 1, and from 0 to 1 it is having 5. So this is actually we can say is something which is given to us. Now in these kind of situation, if we try to if we try to implement the Dijkstra's algorithm, that is not going to be kind of help us here, because it is not suitable when the graph contains negative edges. Here the graph is having negative edges, which is starting from 4 to 3, the edge is asking for a weight of -1, which is obviously negative. So when Dijkstra's algorithm is there, it is not going to handle negative edges, because of the simple reason that it does not revisit the nodes which have already been marked as visited. So even if a shorter path exists through a longer route but with a negative edge, Dijkstra's algorithm will fail to handle it. So it is only the Bellman Ford, it is the Bellman Ford algorithm, not the only one, but it is the Bellman Ford algorithm which is going to help us in these kinds of cases. Now exactly what is happening? So after this initialization, the process which is happening is about relaxation. So relaxing the edges v minus 1 times is going to give us single source shortest path. How? Let us try to understand. So a shortest path between two vertices can have at most v minus 1 edges. If there is even kind of v edges, then it is going to give us a cycle. So a path which is obviously not the cycle is going to between two vertices can have at most v minus 1 edges. Now it is a simple path with v minus 1 edges, otherwise it would form a cycle. Therefore, repeating the relaxation process v minus 1 ensures that all the possible paths between the source and any other nodes have been explored, have been verified, have been covered, have been checked for for finding the minimum path. Now here let us take an example. So assume that we have a node 0 which is a source vertex. Let us see how we can relax the edges here to find the shortest path. So we have the source vertex as node 0, then we have 1, total 4 vertices here. So 0, 1, 2 and 3. So between 2 to 3 the edge is having a weight of 2, between 1 to 2 the edge is having the weight of -1, and between 0 to 1 the edge is having weight of 4. So, this is what the whole situation is. Now, if we try to adopt some process of relaxation on this particular graph. So, in the first relaxation, since the shortest path for vertices 1 and 2 are unknown, we can say infinite, the shortest path between the two the node 2 and 3 will also remain infinite, and for vertex 1 the distance will be updated to 4, because initially when we talk about the distances being updated or distances being initialized to infinity, distance to 0 is 0, because that is the source vertex, that is what is being given in our initialize graph sub procedure which we have already seen. So, distance for 0 is 0. So, 0 plus 4 is going to give us 4, which is obviously less than the current distance of 1, which is nothing but infinity. So, we will be updating the distance for the node 1 to 4 instead of infinity. So, this was kind of the first relaxation, we can say. In the second relaxation, the shortest path for vertex 2 is still infinite, which means that the shortest path for vertex 3 is obviously remain infinite as of now. Now, let us try to relax the edge between which is available between 1 and 2. So, till 1 we have 4, the kind of the distance as 4 which we have updated in the previous relaxation step. Now, 4 plus -1 is going to give us 3. So, distance of 1 which is 4 plus the negative 1 which is the negative edge is going to give us 3. Now, this 3 is obviously less than the infinity which is actually the updated we can say which is the current distance for the vertex 2. So, infinity obviously is greater than 3. So, we are going to update the distance to the node 2 as 3 instead of infinity. Now, in the third relaxation, we will be looking for the shortest path for the vertex 3. So, presently it is kind of we can say the distance from the vertex 0 to vertex 3 is actually infinity, we have not updated it. So, now vertex 3 is going to be updated to distance 2, because till the vertex 2 we are achieving a bound of unit 3 units, and from 2 to 3 it is 2 units. So, 3 plus 2 is going to give us 5, and this 5 is obviously we can say less than the current distance which is presently is being put up as infinity only. So, in the third relaxation, the shortest path of the vertex 3 will be updated to 5, because the distance to 2 plus the edge weight from 2 to 3 which is 2 is equals to 5, and it is obviously less than infinity. So, in this example we have seen that distance to 1, distance to 0 which is from source to source is 0 only, distance to 1 is updated in the first relaxation, then distance to 2 is updated in the second relaxation, and the next one which is distance to 3 is going to be updated in the V minus 1th relaxation. So, we have 4 vertices and 3 relaxation, first relaxation for the node 1, second relaxation for the node 2, and V minus 1 which is 3 here. So, third relaxation for the node number 3. So, in this way we have taken V minus 1 iterations of that relaxation procedure, and now we are able to achieve your we can say this all these shortest path. Now, this was one part of the Bellman Ford algorithm, because this Bellman Ford algorithm essentially gives you, two things. One is the shortest path, the calculation or finding the shortest path, and the second one is the detection of negative cycles. So, till V minus 1 relaxation, it is going to complete the first part, which is giving the we can say shortest path, obviously in the absence of absence of negative weight cycles. But if there is a negative weight cycle, how it is going to be discussed, how it is going to be calculated, that we need to see. So, for detection of negative weight cycles, we need to move one more iteration, or we need to do one more iteration of this relaxation thing. So, if one more additional relaxation, that is the relaxation number width, which is the last node, which is the degree of the vertex set V. So, for example, 4 vertices are there. So, till 3 relaxation, it is going to calculate the shortest path. But for the 4th iteration of the relaxation, if it is possible for any of the edges, this indicates that some edges with overall negative weight has been traversed one more, and this indicates the presence of a negative weight cycle in the graph. Now, just see this whole chronology, that till V minus 1 we are okay. But if we take one more iteration and we are able to reduce the shortest path to some node more, even after V minus 1 iterations of the relaxation procedure, that indicates that some edges with overall negative weight has been traversed one more, and this clearly implies that there is a negative weight cycle which is present in the graph. So, two parts achieved with the help of kind of we can say two different with one particular we can say a loop. For V minus 1 iterations, calculation of shortest path, and for the Vth iteration we will be moving to the calculation of or determination of the negative weight cycle if it is present. So, here we will be taking another example in which here the example is we can say the similar. So, from A to B we have a vertex of this thing, we have an edge of 5, then from B to D we have 2, then from E to D it is -1, from C to E is 1, and from B to C it is 1. And presently, if you can see in this graph, this is kind of the similar graph which we have taken in our previous example. So, here we have given a table of edges as well as a distance array, which is going to be kind of updated with every step of relaxation. But here one more the parameter which is to be updated in the whole Bellman Ford algorithm is about the predecessor. So, that we will be also talking about. Here in this graph we are taking A as the source vertex. So, starting from source vertex, our initialized graph says the vertex from source to source is going to be 0. So, you can watch that in distance array, the distance which is written with A is 0. For B, C, D and E it is infinity. And also have a look at the table of the edges, which is from B to D the weight is 2, which is from E to D the weight is -1, from C to E the weight is 1, from B to C the weight is 1, and from A to B it is 5. So, obviously a presence of negative weight edges is there, but not negative weight cycles. So, that means the problem here is actually well defined. We will not be saying that the problem is not well defined, because the negative weight cycle is not present, although negative weight edges are there. Now, what is happening here also, we will start this was till this figure we can say that we have covered initialize graph. So which is kind of we have said that except the source vertex A, for all other vertices which are B, C, D and E, the value of pi, which is the predecessor, we are keeping them as nil as of now, and for the source vertex the we do not need any of the predecessor as far as distance is concerned, except A, the distance for all other vertices is kept as infinity. And please remember that this distance is distance from the source vertex. So, distance from source to B is infinity, distance from source to C is also infinity, and similarly for D and E. So, this was actually we can say initialization step which we did with the help of a very small procedure which is already covered. Now, in the first relaxation, if you can see that how many checks what all checks is going to be performed. So, we are going to perform all the checks in the same order of the edges, and if the condition holds then the distance will be updated. So, the first check says distance of B plus 2 should be less than distance of D. So, distance of B plus 2 should be less than distance of D. So, distance of B is kind of presently it is we can update it to 5, or we can take it infinity, and then we can do it in the next iteration as well. Similarly, distance of E plus minus of 1 should be less than distance of D. Distance of C plus 1 it should be less than distance of E, distance of B plus 1 should be less than distance of C, and the last one which is the distance of A plus 5 should be less than distance of B. This is the edge which is going to, or this is the updation which is going to happen, because as I have told you that we are going to perform these checks in the same order of the edges, and in the order of the edges was we have started from B to D, then from E to D, then from C to E, B to C, and in the last A to B. So, in this first iteration of relaxation procedure, only the fifth condition which says distance of A, which is 0, plus 5 is less than distance of B, which is infinity. So, this is the kind of check which is going to give us a positive answer, and because of this check we are going to update the distance of B to 5. So, first relaxation of edges has happened, and please notice the situation of distance array or the values in the distance array. So, earlier it was having distance of 0 for A, but for B, C, D, E it was infinity. Now, it has been updated. So, for A the distance is 0, and for B it is 5, for C, D, E it is still infinity, because distance of A plus 5 is going to give you some value which is less than distance of B, which is 0 plus 5 is less than infinity. So, we have updated it. In the second relaxation of edges, if you can see, we are going to update the value of C, value of D we can say. So, from B to D. So, B, the distance to B is 5, and then from B to D we are going to take 5 plus 2 is less than infinity. So, that is 7. So, distance of B plus 2 is less than distance of 7, which is 5 plus 2 less than infinity. Distance of D has been updated to 7. Now, again a relaxation which says distance of B plus 1 is less than distance of C. Now, why we have taken this in the kind of second attempt to the relaxation of edges, because both the edges which is BD and BC are starting from B. So, we have taken the vertex B and relaxed all those edges which are kind of outgoing from B. So, B to D we have relaxed, and we have also relaxed B to C, and till before this the distance to D was infinite, the distance to C was also infinite. That is why both have been kind of updated in this second relaxation of edges. Now, coming to the third relaxation of edges, and that is going to update the distance to E, which is done through the edge of C to E. So, distance to C plus 1 is less than distance to E, which was infinity till this point. So, 6 plus 1 less than infinity. So, distance to E is now being updated to 7. So, now if you can see the distance array has been kind of we can say updated completely. So, for A it was 0 and it is 0, initially also it was 0, but for B, C, D and E at the initial step it was infinity for all, but after third kind of iteration of relaxation procedure, we have B, C, D and E being updated to 5, 6, 7 and 7 respectively. So, this was something in which we have kind of updated the distances from 5, 6 from infinity to 5, 6 7 and 7. But one more set of relaxation is kind of still required here, which is going to be the fourth relaxation of edges, and that is going to update the distance of D from 7 to 6, because there is a shortest path to D which is coming through B to C, then kind of C to E, and then from E to D, because there is a negative edge from E to D. So, because of presence of this negative edge, so if we take distance of E as 7, which was already updated, plus minus 1, which is the weight of the edge going from E to D, is now giving us less than 7. So, 7 plus minus of 1 is less than 7, which is distance of D will be now updated to 6. So, after fourth relaxation of edges, we are going to get this complete distance array updated, but we have not taken fifth relaxation of edges, which is there to detect a negative weight cycle if the graph contains it. So, that is kind of still left. Because of the paucity of time, I am stopping here, and with this figure or with this graph I will be continuing in my next lecture, and we will try to detect the presence of negative edge weight cycles if it is available. Here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. Thank you for a patient hearing. I will see you in the next lecture. Till then, take care. Goodbye.